Hello again. We're going to be looking at a new meter that I just purchased. This is sold by TPI, or Test Products International. It's a TP194-2. Comes in a plain white box. First thing you notice about the meter, it is a lime green with a gray case. The meter is actually made by a Korean company called Summit. Comes with a manual, some probes, a warranty card, and a temperature probe with an adapter. Looks like the adapter for the thermocouple actually has some nice quality to it. This is not at all as cheap as a lot of the thermocouples I see. You can see the rubber grommet in the back of the connector. See on the probes it says UL listed. I spent some time on the UL website and I did double check and made sure that it actually is a listed meter. The tips are threaded. Comes with some nice alligator ends. Looks like these just thread over the top. The boots look nice and pliable. The leads themselves feel real nice. The leads are marked Summit. And it shows here they're 1000 volt Cat 3, 600 volt Cat 4, 10 amp. They have a CE and a UL US mark on them. 3-year limited warranty. Looks like it says this product's warranted to the purchaser against defects in material, workmanship for 3 years from the date of purchase. It says not covered by a warranty, damages to the product which are the result of abuse. So I don't think I'm going to be able to return this meter if I run the tests on it, but that is the plan. One thing I should mention is the manual that they have online is for the 194, not the 2 model, and the manual is different. One of the main differences between the 194 and the 194-2 is the accuracy specifications for the 194-2 is actually quite a bit tighter. Another thing you'll notice on the selector dial here is there's an inductor symbol. So originally they had a 192 meter that had an inductance mode. That's now included on this 194-2. Another one of the unique settings on the meter is this ADP. That's a current probe adapter. I think they offer several different current probes for the meter. You can see there's an optical interface for PC connection. I opted not to get that for this meter. You can see in the lower right hand corner it is UL listed. They claim again Cat 3, 1000 volt, Cat 4, 600 volts. The meter does have logging capability. I can tell you the plastic that they're using on this is actually very good. Look at how well this thing is constructed. You can see the ribbing in it for strength. And I'm putting quite a bit of force on this thing and it's not breaking or having any trouble. It's also got this nice recessed area here where you just slide your finger in and pull it open. Rubber boot feels fairly soft. I've only ever seen 2 multi-purpose handheld meters that would read inductance. This is the second one. Looking in the manual, you can see it has a 50 millihenry range where it can resolve down to 0.01 millihenries. It also has a 300 millihenry range where it can resolve down to 0.1 millihenry. And again, these are 5% plus 50 counts. Okay, so to run this test, you can see I've installed a couple of short jumpers. We're going to start this with a 100 microhenry choke. And we can see it's reading maybe 10 to 20 microhenries. So that's a fair amount of error. This is a 640 microhenry. Looks like it's showing 760 microhenries. This is a 990 microhenry choke. So at least now it looks like we're starting to get a reasonable number out of it. This is just an AC line transformer. The input side is 50 millihenries. I had measured that with my RLC meter. And we can see it reads a little high now, about 55, 56 millihenries. So you can see it's definitely not going to be the replacement of an RLC meter. Typically when I'm using inductors, they're quite a bit smaller. This is a 2.8 nanohenry. This is the largest one I have in my Cal standards. This is a 100 nanohenry. And again, I measure these with a vector network analyzer. So let's do a basic checkout of the meter. We'll see roughly how accurate it is. Most of the resistors that are in this box are tighter than 1%. We'll zero out the meter. So let's try this. This is a 0.01 ohm resistor. So yeah, not too bad for a 2-wire setup. This will be a 0.1 ohm. This is a 0.5 ohm. This will be a 1 ohm resistor. I've taken off the relative mode, and this is a 50 ohm resistor. This is a 100 ohm, 1K ohm, 10K ohm, 100K ohm, 1 mega ohm, 10 meg. Let's try it in conductance mode. This will be a 100 meg. Pretty much dead on. Let's try it with a 1000 meg. Pretty good. Alright, let's try diode mode. This is a short. And here's a single diode. 2 diodes. 3 diodes in series, no problem. Let's try it in capacitance mode. This will be a 150 picofarad. Looks pretty good. If we zeroed this out, it'd be right there. This is a 1 nanofarad. Real good. And 0.1 microfarad. I'll tell you, it looks like there's a bug in the design. So if I go to relative, so I zero out the meter, and I'm going to read a 1 nanofarad. We can see it's basically dead on. And now I'm going to select a 0.1 microfarad. We can see it's overflowed. And I'm going to turn off the rel, and we can see it's still overflowed. I can disconnect the leads, reattach, overflow. And the only way I can seem to clear this out, so I can hit rel, it will not clear that out. I have to take it off the range, and now it'll actually read the correct value. And it does the same thing in resistance mode. Let's try some larger values. So this will be a 1 microfarad. Pretty close. And this will be a 10 mic. Takes a little bit to figure it out. So looking in the manual, it looks like 500 microfarads is the max. This is a 220 microfarad aluminum electrolytic. Let's see if it can read that. Yep, pretty good. 219. On the left I have the Unity UT181. To the right of that is the TPI 194-2. To the right of that the Bryman BM869S. And to the right of that is my newest meter, the X-Tech EX540. This meter had a lot of problems. It didn't work when I got it. I've since repaired it. It still has a couple of quirks, but I don't think it's going to impede this testing. All these are Cat 4 600 volt rated, except the Bryman, which is rated for Cat 4 1000 volts. The TPI is a 50,000 count meter. The Unity 181 is a 60,000 count meter. The Bryman 50,000 count, and the X-Tech is 40,000 counts. All these meters support AC plus DC. They all support true RMS. They're all able to read conductance except the X-Tech. Of course, the only one that can read inductance is the TPI. The TPI is UL listed, so is the Bryman. The Unity 181 was certified by CSA. I know the X-Tech's been independently certified as well. The TPI, the Unity, and the X-Tech are all tri-display. The Bryman is a dual display. Of course, the Bryman and this Unity have dual temperature inputs. The X-Tech and the TPI are a single input. It appears the Bryman is the only meter certified for the EMC standard 61326. For the 50 millivolt range, the TPI is rated for 0.05% plus 5 counts. The 60 millivolt range on the 181 is 0.025% plus 20 counts. The Bryman is 0.02% plus 2 counts. And the X-Tech is 0.06% plus 2 counts. The Unity 181 costs about $300. The Bryman about $230. The X-Tech about $300. And this TPI about $250. So they're all roughly in the same price range. There's a couple of things I don't like about this meter, and I want to show you those right up front. The first problem I see is the volume. And let's compare that against the Bryman. And let's try it with the X-Tech. And now let's try the TPI. So you can see it's just got a very soft sound to it. So for me in a noisy lab environment, this would definitely be an issue. The other thing I don't like about the meter is the backlight. So I just turned it on, and here it's off. You can program the backlight. It's got this edit button. So if you turn off the meter, you hold the edit button, you turn it on, you're in edit mode, and then you can go through the different settings. And this would be your backlight. How long do you want it on for? So currently I've got it set for 1 minute. You can change the value by selecting the rec and comp to select the value you want to change. So if I go to minutes, then I can use the relative and the whole buttons to increment or decrement the value. But it's nothing compared to this Unity where you can adjust the backlight brightness. This is just a very nice display on this. It's too bad it scratches so easily. So it's not too bad in the dark. Definitely has like dark and light spots, and it's darker across the lower and the upper edges. Let's give you an idea of the accuracy between the meters. So currently I have all 4 connected in parallel, and they're attached to a 1 millivolt source. You can see they're all reading reasonably close. This is with a 1 volt signal. And this is with 10 volts applied. Currently I'm supplying a plus or minus 10 volt square wave to all 4 meters. And all 4 meters are set to min max. You can see the 181 with its split display is reading 10.21 for the peak and minus 10.33 for the minimum. Same roughly, it's 10.1 for the max and negative 10.055 for the min. And that's our current value that it's reading. For the Bryman I have to select the rec, and I get the max and the minimum and the average. In the X-Tech again, it's a tri-display. We have our max, our min, and our current reading. At 0.2 Hertz, all the meters are able to read the min-max without any problem. Okay, so this is at 2 Hertz, and again we can see plus minus 10. The Bryman is reading plus 10 and minus 10, average still 0, so no problems there. And the X-Tech again 10.11 minus 10.06. But let's look at this TPI. You can see it's reading 4.9959, so roughly 5 volts positive and negative 4.6. So to get around this, they have what they call a 1 millisecond peak mode, and if we enable that, and we can see now it displays 1 millisecond rec. And now we can see it's reading a little bit closer. It's 9.56 and negative 9.58. So it's still not quite right. It's a vast improvement, but I don't understand what this 1 millisecond peak means. Again, I wrote TPI, and they explained that that's basically sampling at 1 millisecond. And I would have imagined with a 1 millisecond sample rate, this would have no problem reading the min-max on something this slow. But as you can see, it can't quite do it. And if I take that frequency up any higher, this is just going to get worse. So this is at 4 Hertz. We can see it's reading 7.9 and negative 7.9. This is with 8 Hertz applied. And we can see it's now reading positive 5.2, negative 5.2. The Bryman is now reading negative 0.2 and positive 2.5, and the X-Tech is reading plus 5.6 and negative 5.6. Now the Unity on the other hand is reading plus minus 10 still. The Bryman has this crest mode and it can easily detect this signal. We got our max 10.31, negative 10.31. So it's definitely capable of picking this up, but this TPI can't do that. Again, I'm not sure what this 1 millisecond peak is all about. I don't know if they have a filter on the front end when you're looking at the DC voltage or not. But again, for the TPI, there isn't a separate crest function or anything like that. Currently, I'm supplying a 1 volt 50 Hertz sine wave to all 4 meters. You can see the X-Tech is reading 50 Hertz roughly. Ryman 50 Hertz on the X-Tech as well. What I'm going to do is increase the frequency, and let's just see how this meter rolls off compared to the other 3. This is currently at 1 kilohertz. This is at 2 kilohertz. This is with 4 kilohertz, 8 kilohertz. This is at 20 kilohertz, and we can see the X-Tech now is rolling off pretty quickly. It's at 40 kilohertz. 80 kilohertz. It's with 200 kilohertz. This is with 600 kilohertz. We can see the Bryman now is reading 0.6 volts. This is at 1 megahertz. We can see the Unity now is reading 0.81. The Bryman is now 0.17 or so. This is at 1.2 megahertz. We can see now the TPI is starting to roll off pretty quickly. Just looking at the frequency counter for each meter, I'm currently supplying a 5 megahertz sine wave. You can see they're all reading roughly 5 megahertz. And I'll go ahead and increase that just slightly. This meter is actually only rated for 5 megahertz, so I expect it's going to roll over. Yep. Yeah, so again, 5 megahertz, it's pretty good. If you're interested in knowing where this X-Tech falls off at, let's have a look. 7. So that's 15 megahertz. That's the upper end of this generator. So I've gone ahead and attached this to a different RF generator. I've gone ahead and switched ranges. Let's just go ahead and continue taking it on up. Okay, so there's 49.5 megahertz. Let's just see if it'll roll over at 50. I'm not sure if that beep was a rollover. That's right, about 72.7 right there. Of all the meters I've tested, I believe that that's the highest frequency I've been able to read with a counter. All 4 meters are selected for AC plus DC mode. We can see on the UT181 we have the AC value, the DC value, and the AC plus DC. Same for this TPI 194.2. We have the AC, the DC component, and the AC plus DC. On the Bryman we have the AC plus DC and the AC, and on the X-Tech we have the AC plus DC. Next, what I'm going to do is full wave rectify the signal, and we should have the same value on all 4 meters less the drop of the rectifier. So we can see our AC content on the 181 is 16.5, 16.5, 16.5. On the X-Tech we have to deselect the AC plus DC. This will give us our AC content, and we select DC, and this would be our DC content. Same thing with the Bryman, we deselect the AC plus DC. This is our DC content, so 33.8, 33.8, 33.8, and roughly 33.8. So it looks like the TPI has no problems with this. Before I forget, one of the features I want to show on this TPI is this hold function. You'll see when I select hold, I get a 1 hold, 2 hold. I've just got a battery pack, and I'm going to attach the meter to that. And we can see once it gets stable, it's recorded the 2.8105. And then if I do it again, you can see how it kind of round robins this. So it's pretty nice. You can actually view 2 different hold numbers. You can see all 4 meters are set to volts AC. Currently this is a sine wave being applied to all 4 meters. I'm going to change that. This is now a triangle wave. This is a square wave. This is a sawtooth. Looks like they all do basically the same with the 4 different waveforms. Currently I'm supplying a triangle wave to all 4 meters. Look at this on the X-Tech. Compare that with the Bryman. See how this thing just jumps? Now let's look at the TPI compared to the Bryman. See how it's skipping? Yeah, the bar graph on this is very slow. This is a real nice feature. So, you know, it's got plus or minus 6. What I'm going to do is increase the frequency a little bit. You can see how bad this TPI is skipping now. Again, here's the Bryman. Very smooth. The Unity has basically about 3 steps is all now. Currently we're at 0.5 Hertz. Again, you can see the Unity, it's very smooth. The TPI is getting much worse now. Of course, the Bryman is very smooth. This is at 2 Hertz. And it looks like the TPI is just aliasing like crazy now. See the Bryman again, no problem with this at all. The X-Tech almost looks random now. This X-Tech in the 194, really no excuse for this. Both these meters, fairly expensive. You think if you're going to put a bar graph in, you'd make it work. Currently all 4 meters are connected together in series. I'm supplying a roughly 7 microamp current through all 4 meters. And you can see they're all reading roughly the same value. We'll go ahead and increase that a little bit. So all roughly 282 microamps. Let's go up a little bit higher. So roughly 975 microamps each. This is with roughly 1.4 milliamps. Let's go ahead and we'll select the milliamp range. So again, all reading roughly 2.4 milliamps. So the X-Tech has a 4 to 20 milliamp conversion built into it. So if we select 4 to 20, we'll get it in percentage plus current. Same thing with the Bryman. You can actually see it in the upper right. The TPI does not have that feature. nor does the unity. Here you can see we're supplying roughly 70 milliamps. We're at roughly 265 milliamps. Currently we're supplying roughly 335 milliamps. Let's try them in the 10 amp scale. You notice with the TPI it does not have a way to detect the lead being in the wrong connector. Of course we'll see that with the Unity. You set it to amps. You have to have the leads plugged into the amps or you're going to get a lead error. The Bryman's kind of nice. You notice if I have it on the amps mode, if I move the lead from the milliamp jack to the amp jack, it'll just automatically switch. Unfortunately, the X-Tech, like the TPI, has no way to detect the lead fault. You can see currently I'm supplying roughly 1.7 amps. And this is the top end of my bench power supply that I'm using, so roughly 6 amps. Okay, so both meters are again tied in parallel. And you can see I've got the high voltage power supply out. We're going to be subjecting both of these meters to a DC voltage. I thought for comparison we'd use the X-Tech because I hadn't used this meter yet at high voltage. So let's just go ahead and we'll turn it up a little bit. And again, this is the upper limit of this power supply, so almost 1 kV. Neither meter having any problems with this. You notice the TPI 194 has gone to sleep. Some meters you have to actually turn the dial on and off. Okay, so I've got the high voltage probe out. You can see it sitting here. It's attached to our oscilloscope. And what we're going to be doing is applying a AC waveform. And you can see we're roughly 540 volts RMS. What I'm going to do is increase our offset. We'll see what effect this has. You can see here on the scope, ground is our center line up here. It's basically as high up as I can make it. You can see we're still at 544, 540. It's interesting. I don't know if that meter is breaking down with this. And you can see I've biased it negative. Both meters reading roughly the same value still. We'll go ahead and zero that out. You can see it's basically centered now. And let's go ahead and increase the frequency. This is roughly 3 kilohertz. You can see it's peaking up a little bit. And it's funny how this meter just kind of overranges there for a second and then it recovers. Not quite sure what's going on with that. Okay, but no real problems with either meter. They seem fine. So I wrote TPI about my suspicions of there being a bug with the rel mode. And they wrote back and said if you push it for a short time and it'll enable it, and you push it for a short time again, it'll disable it. So you can see if I push it for a short time, it enables the rel mode. Push it for a short time again, it's disabled. Enabled, disabled. No problem, right? So let's just clear it out. So I'm going to take it off of ohms, put it back into ohms. We'll touch the two leads together. We get some value. I'll go ahead and select rel. Okay. And now I'm going to attach it to a 100 ohm resistor. You can see it reads OFL. We'll try it at 50 ohms. You see it reads right. So no problem there. Now I'm going to deselect the rel. You can see it's off of the rel mode. I'll reattach our 100 ohm resistor. It still will not read correctly. We'll attach it to our 50 ohm. You see it reads correctly. The rel is not being displayed. Let's try it for a long hold. Now it's in log mode. Let's try a long hold again. It's out of log mode. We'll go back to our 100 ohm. It will not read it. Again, the only way I can clear it, I'll go to millivolts, for example. Back to ohm mode, and there we go. So 100 ohms. So I wrote TPI about this problem, and they pointed out something that I had not realized. You notice I have the meter in resistance mode. I'll go ahead and short the two input leads. I'll select rel. And there's our new reference number. And I'll select our 100 ohm resistor. You can see it's out of range. And we'll deselect our rel mode. And you can see it's still out of range, which is the problem I saw. But the thing I didn't notice is when I selected the rel mode, it took it out of auto range. And when I deselected the rel, it didn't place it back into auto range. So to get it back into auto range, you have to hold down the range selector. And you see it switches back to auto range, and there's our value. So this is the first meter that I've ever seen where when you take it out of rel, basically it just doesn't reset the meter back to normal mode. But it's something to remember. It's not called out in the manual. So unless you're paying attention to what's showing on the screen here, you could miss this. This meter has data logging available, and that's activated by pushing the logging button. Before I do that though, I want to show you some of the data I just collected. So I had the meter logging resistance. I can scan through those values using the up down arrow keys. So you can see changed it to 100K. But check this out. I mean, what does that even mean? So let's just go ahead and start a log. The way we enable it, we push the rel mode and we hold it for a long time. You can see again it enables the log. I can attach a resistor. And we can put in another resistor. And we'll do another one. You can program the time interval and such. It's basically all programmable through that setup menu. Once you're done logging, we just push the rel button again. Takes it out of the log mode. So if we want to view the data, we just select edit. We hold that until it goes to log mode. And then we can again use the arrow keys. Oh, there we go again. Look at that. Looks like it's trying to show a 2 possibly, period, 3 period. Wow. It's almost like they're storing the ASCII data from the display and it possibly hasn't settled. I mean, that's what it looks like to me. So like here it may have done an auto range. So you get the 2 decimal places. Wow, that's not very useful. Let's go ahead and look at the continuity test. You can see it's non-latching type. So I've gone ahead and made all the measurements for the continuity tester. The open circuit voltage for this meter is 3.07. The short circuit current is 965 microamps. The short circuit resistance is 42 ohms. It opens up at 43 ohms, so no hysteresis at all. With a 2 Hertz signal, I'm able to go down to 2 milliseconds and it's still able to detect a short. And using a 50% duty cycle waveform, I can go above 10 kilohertz and the meter will still detect it. So this meter is actually very similar to the UT90A's continuity tester. I'm sure you're all wondering what this looks like on the inside. I know I am. So let's just go ahead and take this thing apart. So it comes with a Duracell battery. It has two little fuses in it. You can see fast acting, 1000 volts, 440 milliamps. It's got its own little separate blast shield area. All metal inserts. Looks good. I wonder if the inside of it looks this good. If it does, I'm going to be very impressed. I can tell you, I'm not a big fan of the 9-volt battery, especially on a meter like this. They're claiming 50 hours of battery life with this meter is it. That is nice though. You see how they've got this recessed area for your fingers to grab that? It's like no problem just getting a hold of that battery, popping it out of there. That's a nice setup. You can see they've cut some slots in here for creepage. See how this shows up, but there's various ones that look like around the selector switch. There's 3 of them here. There's one here, along here. You got this T-cut here. But I don't see any transient protection. You can see it's got a little coin battery up here. Again, that's for the real-time clock on this meter. When you're using the data logger, it'll actually timestamp the data. Maybe a little hot glue or RTV holding the crystal in place. Well, let's have a look underneath this. Let's see what it looks like. Not sure what's going on with a little foam here. They've got the spring contactor sitting inside of this area. If you're looking at how that X-Tech cracked, let's have a look at this switch. Boy, look at that. It's got a metal insert in this thing. Again, from a mechanical standpoint, this is very nice. This is definitely one of the better made cases I've seen. You can see they have 1, 2, 3, 4 PTCs, and it looks like a single MOV sitting here with a high voltage capacitor. You can see our shunt down here. If I hold the meter up to the light, I can see the trace coming off of the input, and it actually runs right down the center of this cut. So they're really trying to get some isolation around this thing, and then you can, I don't know if the camera will show this, but I can see it right here. It breaks off to the switch, works its way up here to, looks like TU9. I'm not even going to guess if this meter is going to survive or not. The plating on it looks real good. Looks like it has a little bit of flux residue left on it. It's a little sticky. But the quality of it looks pretty good. Part on the right here is marked by JRC. Appears to have a part number of NJU6436F. The other part looks like it says D78F0034BGC. Looks like the part down here is a small programmable memory by Microchip. Looks like it has a few trimmers. These are all capacitors. I don't see any other trimmers on the board. I wouldn't expect there to be. Looks like somebody at the factory was not being very careful the day this meter was built. See that? They chipped that connector. I believe that that is probably where they're doing the cal from. But broke that corner right off. Looks like the board is marked LDT-M94V-0, and then it has a E337137. You can see here, it's kind of interesting. There's another push button here, and you notice underneath it, it says cal, and I'm assuming that's how you enter the calibration mode. Looks like to get under the can I would have to unsolder it. I don't think I'm going to go that far. I don't think I'm going to lift the display either. We're just going to clean up a little bit of that flux residue while we've got it apart. So black that is. So this little device down here, this is a little NTC. So yeah, the quality of this meter, at least from an assembly standpoint, looks pretty good. I've definitely seen a lot worse. Because I've just gone ahead and installed the battery. Let's just see what this sounds like with the case off. Not too bad. I think the case is actually so good it muffles that speaker too much. It's pretty nice without the case on. It's about the volume I would want. Get a little bit more flux off of this. You just see the on the swab there. Yeah, that's not my fingers causing that. See all that? Alright, I'll go ahead and functional test this and make sure it's okay. TPI checks out just fine. This video is starting to get a little bit long. I'm probably getting close to an hour right now, so I think we're going to cut it off at this point. Our next step is to start transient testing the meter. We'll start with using the transient generator and we'll do some AC line tests with it. Next we'll use our grill starter to static test it. I'm sure many of you saw what happened to this Unity 181A. This one failed on the very first hit with this grill starter. And unfortunately, this TPI 194 is not rated for that EMC standard that calls out the static discharge test. You would think that pretty much any meter that you bought that you were spending more than $200 on, it would be certified to pass that test. Hopefully the TPI won't behave like so many of the Unities and the Vichy where they fail on ESD. So that's going to be it for this video. I hope you all enjoyed it. I'd like to welcome any of you new members who've just joined up. Glad to have you aboard. If you're interested in seeing how robust meters like this are against other meters, this is definitely the place to come. All these meters are tested the same. I use the same transient generator with the same waveforms, and I typically will test these meters to failure. So stay tuned for part 2 of my review of the TPI 194-2. Later. One hit. God damn it. Dead. She is dead. So I'm using a LaCroix 8500A. This is a 5 gigahertz front end, and it samples at 20 gigasamples per second. When I ran this thing, which I had done before, unfortunately I hadn't saved the data for it, so I repeated the test. But with a direct contact, this igniter only puts out about 1 amp peak, and the pulse width is only about 5 nanoseconds total. So if we look at our graph, basically what we're seeing coming off of this gun is going to be a little 1 amp peak, and it's going to decay here within 5 nanoseconds. It's not a whole lot, but long and behold, some meters do fail with it. So while on the internet, you'll read in a lot of forums, people will talk about the safety of the meters. I really am more concerned about the robustness. I don't want a meter at home that I hit this thing with a real simple static discharge and it destroys the meter.